Hello students, how are you? I hope you are well and safe. I welcome all of you on this educational platform. Students, today we shall start the new chapter, that is periodic table and periodicity in properties. Students, it is very important and fundamental unit of inorganic chemistry. If you have command on this chapter, you can have command on the entire inorganic chemistry. And periodic table is something very important. Today, I will discuss about the history of periodic table with you. How periodic table have been developed over the course of time. It was developed in so many years. So, what are the historic models of the periodic table? And what about the modern periodic table? That we will discuss in today's session. So, let's start historical models of periodic table and modern periodic table. History of classification and modern periodic table. See, periodic table was never developed in a single day. It is a long process. So various concepts are there in which we try to classify the element. But the first basic question which comes in our mind, that why do we need classification? Before going to this chapter, let me ask you some question. Is alphabet necessary to learn any language? And the right answer is yes. You cannot learn any language if you don't learn the alphabets. Say for example, you want to understand the Telugu language. So what do we need to understand the Telugu? In order to understand the Telugu, we need Telugu alphabet. Similarly, if you want to understand the English language, then you need to learn the English alphabets. Similarly, based on this fact, some scientists considered chemistry as a language, and periodic table and its alphabet chart is the alphabets for the periodic table. See, these are the different elements which are arranged in the tabular form in this periodic table. What you see in front of you is the modern periodic table. This periodic table, as I told you, was not being developed in a single day. So we have some historical classification. There is a gradual growth in the chemistry with the discovery of element by the scientist. You will be surprised to see that in 1800s only 31 elements were there, but in 1865 there were 63 elements identified, and at present we know about 114 elements. So what are the objectives of this chapter? What are the objectives of this class? Once you will complete this class and complete this chapter, you would be able to understand the need for classification of elements. Why we need classification? You would be able to understand the present form of the periodic table called as modern periodic table. And you would also be able to understand the blocks, S block, P block, D block and F block. And you would be able to understand the periodic trends. So what are the periodic properties and what are the trends? You would be able to understand. So if I ask you a very simple question, why do we need to classify elements? Why? You know guys, at present we know about 114 elements and millions of the compounds. So it is very difficult for us to study all the elements at the same time. So in order to understand the properties of the element easily, what we did, we tried to classify them systematically. So periodic table is nothing, it is just systematic arrangement or the classification of the elements. So first we shall discuss about the genesis of periodic table or classification. First we will discuss about the 𝕆𝕋ℍ𝔼𝕼's law of triad. Then we will go for the Newland's law of octave. Then Lothar-Meyer periodic table. Then Mendeleev's periodic table, and it will be followed by the modern periodic table in the end. So the picture you see here is a John 𝕆𝕍. What he did, he gave the law of triad. He noted that similar properties of several group of 3 elements called as triad. He formed group of 3 elements together, and he also found that if average of atomic weight of first and third element, if it is equal, if average of the atomic weight of first and third element is equal to the second one, then they will have similar properties. Like atomic weight of lithium is 7, for potassium it is 39, and the average of them is 23, which is equal to sodium. So the properties of lithium, sodium and potassium are somewhat similar to each other, right? These are some other examples of 𝕆𝕍𝔻 law of triad. You see in this example, atomic mass of calcium is 40, while of barium it is 137, and the average of this is equal to the strontium. The same happens with the chlorine and iodine. Average of the atomic mass of chlorine and iodine is somewhat similar to the bromine. Then after this law, there was a development of Newland's law of octave. Octave means 8, and 𝕆𝕍𝔼𝕻's classification of periodic table. See, he is a John Alexander Newland, and he gave the law of octave. You know about the music, guys? Do you know the notes of music? Have you ever heard the music? Sa re ga ma pa da ni sa. See, in this, these are the 8 notes of music, and each 8 note is somewhat similar to the first one. Sa re ga ma pa da ni, and then again sa. So he arranged the element in the increasing order of their mass and found that, like the notes of music, each 8th element is similar to the first one. So that when elements are arranged in the increasing order of their atomic weight, he found every 8th element had the properties exactly similar to the first element, like the modes of music. Like I said, sa, re, ga, ma, pa, da, ni, and then again sa. So it is like the 8th note of the musical scale. Now you see, if you choose any element, say for example you choose lithium, then 1, 2, 3, 4, 5, 6, 7, and the 8th, that is sodium, is similar in properties to the lithium. So this arrangement of the element in the similarity is called as Newland's law of octave. Now what about the 𝕆𝕍𝔼𝕻 periodic table? There was a scientist, 𝕆𝕍𝔼𝕻. He basically formed a curve. He plotted the physical properties such as, what are the physical properties? Atomic volume, melting point, boiling point against the atomic weight, and he obtained a periodically repeated pattern, a bell-shaped curve, which is repeated periodically. But it was not published before the work of Dmitry Ivanovich Mendeleev. He was a German chemist and classified the element on the basis of their atomic weight and a plotted curve between atomic weight and atomic volume. Then here comes the Mendeleev's periodic table. He was a Russian chemist. His name was Dmitry Ivanovich Mendeleev. He said that the properties of elements are periodic functions of their atomic weight. Now you must be thinking, students, what is periodic function? See, periodic means the properties which are repeated in the certain time, and function means proportional, having relation. So like when you go to the school every day, suppose let us say at 7 a.m. you go to the school. So you go to the school every day just after 24 hours. Every day at 7 a.m. you go to the school. So it is a periodic function, because going school is a kind of activity which is repeated exactly after 24 hours. So that is periodic function. So he said that the properties of elements are periodic function of their atomic weight, and he was the first one who constructed the periodic table in the tabular form. Before Mendeleev, someone from triad, Newland gave the octave, 𝕆𝕍𝕻 gave the curve, but no one ever formed a tabular arrangement. So he was the first one in the history of the genesis of periodic table who arranged the element in the tabular form, in the form of table. So basically, this was the arrangement of Mendeleev. In this, there are two types of columns. The vertical columns, these are the vertical columns, and these vertical columns are called as groups or families. Why families? Because they have similar properties, and you know, we expect the members of family will have similar kind of properties. So these vertical groups or columns are called as groups, and they are families as they have similar properties. What about the other columns? Now you see, these are the horizontal columns, and these horizontal columns are called as periods. So these horizontal columns are called as periods, but they are not called as family, remember, because property is not similar in the periods, but property are similar in the groups. So these horizontal row are called as periods, which are 7 in number. And what about the groups? They were 9 in number. He also did one thing. He predicted the existence of unknown elements and left some gaps, naming them as the 𝕐 element. 𝕐 means having similar properties. Like when he gave his periodic classification, gallium was not discovered, but he predicted that one day gallium will be discovered, and instead of gallium, he used the term 𝕐 aluminium. Means there will be an element having properties similar to the aluminium, and this element 𝕐 aluminium was later discovered in the form of gallium. Similarly, he used the term 𝕐 boron. Means this element will have similar properties like boron, and later it was discovered as scandium. The same thing he did with the germanium, where he said 𝕐 silicon, which was later discovered as germanium. He also did one thing. He corrected the atomic weight of beryllium and indium based on their valency. Say for example, before Mendeleev, we used to take atomic weight of beryllium as 13.5, but actually it was 9. It was Mendeleev who corrected this mistake. He corrected the atomic mass of beryllium and indium, right? Now some elements with the higher atomic weight were placed before the low atomic weight element in order to maintain the similar chemical nature. This was the drawback of Mendeleev's periodic table. See, Mendeleev's periodic table was based upon one law. Which law? That elements should be arranged in the increasing order of their mass or atomic weight. So you have to keep lighter element before and then after heavier element. But in order to keep the similar elements together, he broke his own rule. Mendeleev broke his own rule deliberately, knowingly he kept lighter elements after the heavier elements at some places, and that is called as inverted pair or anomalous elements. This was the drawback of Mendeleev's periodic table. Also, the position of hydrogen was not made clear. In the classification of Mendeleev, position of hydrogen was not at all clear. Although it is still not clear in the modern periodic table, but it was also the drawback of Mendeleev's periodic table. In the Mendeleev's periodic table, position of lanthanoids is uncertain. But in the modern periodic table, there is a certain position for the lanthanoids. So this is also one of the drawback of Mendeleev's periodic table. Now hereafter, Mendeleev's periodic table, we shall discuss the modern periodic table. So who gave the modern periodic table? Who gave the modern periodic law? The modern periodic law, which I will tell you in the next slide, is based upon the experiment of the scientist Henry Moseley. He found that atomic number Z can be related to the frequency of the X-ray emitted by using, where A and B are the constant in this equation. So basically, atomic number is related to the frequency. See, frequency is a physical property. So somewhat he think that instead of atomic mass, which was taken in the Mendeleev's periodic table, we should use the atomic number. So by using this experiment as a conclusion, we gave the modern periodic law. And what is modern periodic law? It is physical and chemical properties of elements are periodic function of their atomic number, because atomic number depends on physical properties, or you can say vice versa, that physical properties primarily depend upon atomic number instead of atomic mass. So here is the modern periodic law. The physical and chemical properties of the element are periodic function of their atomic number and also electronic configuration. This simply means if you will change the atomic number or the electronic configuration, definitely when you will change the atomic number, electronic configuration will eventually change. So whenever there is a change in the electronic configuration or the atomic number, there will be change in periodic properties and physical and chemical properties. So this was the basic law behind the modern periodic table. This is the modern periodic table, students. In this modern periodic table, we have 18 groups or families. These 18 groups or families are given the name 1, 2, 3, 4, 5 and up to 18. There was an old notation of groups which was first A, second A, third A, fourth A, then fourth B and fifth B, 6B, 7B. Then these three groups are collectively called as 8th group. Then first B, second B, which is followed by third A, fourth A, fifth A, sixth A, seventh A, and finally 0, which is now called as group 18. So there are 18 groups and vertical columns. 18 groups or the vertical columns or the families, and there are 7 periods which are horizontal rows. So this is the modern periodic table, or also called as long form of the periodic table. Here you go. This is the modern periodic table in which you see all the periods and groups are arranged. See, in this periodic table, position of hydrogen is still uncertain. In the first period, there are only 2 elements, hydrogen and helium. In the second period, there are 8 elements. In the third period, there are 8 elements, while in the fourth period, there are 18 elements. And the number increases thereafter. In the modern periodic table, there are different blocks. Middle of the periodic table is D block, also called as transition elements. They have general outer electronic configuration n-1, d1 to 10, ns 1 to 2. Means their outer shell will contain 1 to 2 electron in s subshell and 1 to 10 electron in penultimate d subshell. They are all metals. No d block element is non-metal or metalloid. and they mostly form colored ions because they are paramagnetic in nature due to the presence of unpaired electron. They exhibit variable oxidation state. Do you know what is variable oxidation state? You must have seen the iron +2 or iron +3. So iron can exhibit +2 or +3 oxidation number as well. This is called as existence of variable oxidation state. They also show paramagnetic nature because of the presence of unpaired electron, and because of their variable oxidation state, they can be used as catalyst. In fact, D block elements are very good catalyst. What are the catalysts, students? Catalysts are those agents which enhance mostly rate of a reaction and they remain unchanged in the end of reaction, both quantitatively and qualitatively. In both the aspect, they remain constant. Then another is F block element. F block element are also called as inner transition elements. These are the elements in which differentiating electrons are entered in the n-2 F subshell. It is not outer shell, not penultimate. They go in the pre-penultimate n-2 F subshell. That is the reason why they are called as F block elements. And this is their general electronic configuration. Outer shell will contain 2 electrons. Penultimate shell, D subshell, will contain 0 to 1 electron. That is also incomplete. And pre-penultimate shell, n-2, contain 1 to 14 electron in their F subshell. Alright. These are lanthanoids. So what are lanthanoids? All the element which comes in 4F subshell and placed after 57 number lanthanum are called as lanthanoids. So lanthanoids basically ranges from 58 cerium to 71 lutetium. You can see lanthanoids in front of you. Then what about the actinoids? Actinoids are those which are placed after 89 number actinium. They are from element number 90 to 103. 90 number thorium to 103 lawrencium. These 14 elements in which electrons are filled in the 5F subshell are called as actinoids. So we have two series. One is lanthanoid, another is actinoid, and collectively they form F block. So F block consists of 2 rows, lanthanoid and actinoids. Then these all are metals, and most of the actinoids are radioactive elements. They are not stable as they are radioactive. And the most common oxidation state of the inner transition elements, which is lanthanoid and actinoid, is +3. So +3 is the most common oxidation number of F block element, we can say in broader ways. And the element, all the element which comes after uranium, see here is the uranium 92 number, and after the uranium there is an neptunium 93, and all other elements from 93 neptunium to 103 lawrencium, they are collectively called as transuranic elements, which comes after the uranium. Now there is one more term which we want you to understand, is the diagonal relationship. So students, what is diagonal relationship? What is diagonal relationship? See, in the family first A, which is also called as alkali metal, there are elements like lithium, sodium, potassium, rubidium, and cesium. And definitely it is a family. So we expect that properties of lithium, they resembles to the other members of the family. But in some properties, lithium do not resemble with the other members of the family. Instead of that, there is an adjacent family, second A, and the members of second A are beryllium, magnesium, calcium, strontium, and barium. Lithium show resemblance with the diagonally opposite member of the adjacent family, and this relationship is called as diagonal relationship. Similarly, in some properties, beryllium resemble with the another diagonally present member of the adjacent family, which is aluminium. So in some properties, lithium resembles magnesium and beryllium resembles aluminium. This relationship is called as diagonal relationship, in which member show resemblance with the another member present diagonally. Right, students? So this was about the genesis of the modern periodic table and the historical development of the periodic table. In the next section, I'll tell you about the periodic properties. So this is it. I hope you liked today's lecture. Please keep coming and keep studying.